So we're from Georgia Tech. My name is Miles Turner,
I'm Tatum Hardy.
I'm Taha Karati. And I'm Josiah Todd.
and we are presenting on exploring and utilizing lunar lava tunnels on the moon. So this is just a brief agenda of what we'll be covering today. So first, starting off, we'll state the problem and our idea of how we are going to go about a solution. The second part will be showing how we arrived to our solution. It's going to be a decomposition. Then we'll do a trade study on a few key components of our solution. And then finally, we will show you our solution in our concept architecture.
So the overview of the actual problem is to establish a permanent base on, permanent human base on the moon, and more broadly to explore lunar lava tunnels. Challenges include human survival by extracting oxygen and water from rocks, being shielded from solar radiation and ions, and being able to survive in extreme temperatures.
So just to give you a little bit of background information on our stakeholders for the project, it's going to be NASA Glenn Research Facility. They're a government facility located in Cleveland, Ohio. Every year they actually have university student design challenges, this being one of them, in hopes of stimulating out-of-the-box innovations from university students, as well as helping further their research and technology for future missions.
The goals and objectives of our specific mission include not just finding the lunar lava tunnels, but also understanding their composition, also evaluating potential locations for the human habitat base. We need to be able to do this with minimal mass and tools, equipment, structures, and be able to minimize physical interaction with humans. More specifically, the objectives are to create an autonomous robotic system that can enter, explore, and map the subsurface of the tunnels. Also to collect information for human habitat evaluation. This will be in the form of samples. And to create concepts for how to robotically construct a habitat in an underground cavity.
So this is just a little brief concept of how we're going to get to our part of the mission. We will, once we complete our systems, we're going to prep for launch the systems into a low Earth orbit, doing moon transfer to a moon parking orbit, and then from there we will have a lander land inside a lunar lava tunnel.
Broken down even further, we will have the lander land. It will quickly deploy some solar panels to generate power. It's going to scan the surrounding area and do all sorts of measurements. It will transfer that data back to Earth, and Earth will use that to 3D model the tunnels.
And then spawning off of that, we will actually be comprised of two systems, the second system being our rover. Our rover will disembark from the lander, which will then explore parts of the lunar lava tunnels that the lander could not explore. It'll collect a lot of the similar data as the lander, then return back to the lander and transfer data if needed, and recharge its batteries if needed, and then continue to explore more of the lunar lava tunnel.
A more detailed description of the concept of operations for the lander is that first the lander needs to land, and then it deploys its solar panels and stores power. After this, the lander needs to survey the area, which it will take pictures of the surrounding area, collects temperature fluctuations, collects seismic activity, and then collects radiation fluctuations. That then all that data will be sent back to Earth, in which then Earth uses the data to create a 3D model of the moon's lunar lava tunnels. The data collected helps with determining the location of potential lunar base, and the data collected helps to see the resources in the area.
So here's a more detailed concept of operations for the rover. The rover deploys from the lander. It does a safety check of all its subsystems. It starts to explore the lava tunnels, taking pictures, collecting samples of lunar regolith, using laser systems to map out the tunnels, collecting temperature fluctuation and radiation fluctuation data inside the tunnel, and then returning to the lander. It'll use its autonomous functions to do so. It'll transfer the data to the lander. It'll recharge lithium-ion batteries from the lander's power supply. It'll then begin a new exploration of the lunar lava tunnel. So here's some top-level requirements for the whole system. The rover and lander will have a lifetime of 1 year with the ability to explore up to 5 miles of the lunar surface. around the kind of landing area. The cost of the mission shall not exceed $1 billion. The mission will be operational by December 1st, 2025.
So just to help with our understanding and kind of approaching this mission, we did a morphological matrix over the entire mission. With it, we talked about how many systems we would use, the types of systems being used, such as a rover and a lander. We talked about the range in which we would want to be investigating, the power sources, the navigation, and the communication subsystems, as well as the data collection part of our systems.
A more specific view of the lander's morphological matrix includes subsystems for power, communication, structures, heating, navigation, and landing. Here we explored the most probable options for such subsystems and narrowed down what our decisions would be.
And identically, we did the same for the rover, with its key subsystems being power, communication, structures, heating, navigation, and movement. Again, we just laid out all the options and ideas that we could come up with to help us kind of grasp with a solution for this mission.
Even deeper level of detail, we created n-squared diagrams for both systems. This is the lander's n-squared diagram. It includes the systems of power, communication, structures, heating, navigation, and landing and data systems. It includes functions from optimized component heating systems to element positioning data and relaying data back to communication systems, everything.
So, again, we did a n-squared diagram with the rover, with its key components being power supplies, sensory controls, movements, drills, spectrometer, communication systems, and relay control. We're just showing how everything will hook up and how the compatibility of it will be. As you can see, there's going to be a lot of feed-forward data, but not as much feedback data, so it should be a rather quick acting system, which can then transfer its data to the lander to be transferred back to Earth.
The flow-down requirements for all the systems are first and foremost to be able to operate in microgravity, to be able to work between a range of negative 100 degrees Celsius and positive 120 degrees Celsius. It needs to be able to operate autonomously, be able to withstand radiation, and be able to withstand moon dust. The flow-down requirements for the lander specifically are that it needs to be able to generate enough power for itself and the rover. It needs to be able to test and interpret the data given by the rover. It needs to be able to move short distances and relay its information back to Earth.
And then the flow-down requirements for rover will the overall one will be to be able to explore the entire lunar lava tunnels. To do this, the requirements will be to store enough power for its excursions off away from the rover. It shall be able to drill and collect moon regolith. It should also be able to move across varying terrain from 0 to 45 degrees and do this while operating autonomously. It should also have the ability to communicate directly with the lander or other systems on the moon as well. And it shall also be able to collect the data and store it so that it can transfer back to the lander itself.
We conducted trade studies to help us pick out of our 4 best or most important subsystems, being power supply, communication, navigation, and movement, to help us pick out what our best options are for each subsystem. For power supply, our main criteria is resiliency, cost, availability, ease of use, efficiency, and lifetime. Being resiliency and lifetime are more important or more weighted criteria. And from those that we can see is that nuclear energy, rechargeable lithium ion batteries, and solar power being the more preferable choices. Our next one being communication, our main criteria being reliability, cost, development stages, latency, and mission success, being reliability being our more important criteria. And from our options, it would seem that the X-band waves and radio waves being our more preferable options.
So here's a trade study on our navigation. We had a few criteria listed here: accuracy, cost, development stage, time and communication, autonomy, and mission success. And accuracy, autonomy, and mission success were weighted the highest. And of the 4 options we had: radio navigation, locus-based navigation, satellite navigation, and inertial navigation, we chose to go with inertial navigation via some sort of accelerometer or other type of sensor for our navigation. Here's a trade study on movement. Our main criteria for movement were cost, agility, development stage, reliability, and mission success. And our reliability, mission success, and development stage were the main kind of criteria there, the most weighted.
The conceptual architecture for our lander being what it looks like. It's roughly the sizes of a car with 2 large solar panels. The interesting features of the lander is the solar panels on both sides to help recharge the energy. The wheels, so that way it can move around and stay inside the solar power to keep the solar power. And then also has other components on the inside to allow it for gathering data and deploying the rover. Why this is a great concept is that it acts as a home base for the rover, as well as to be able to transmit communication. It power supplied to other local systems, and multiple rovers can be stored inside the lander. These are the bottom, top, and side views of the lander, and basically what the lander looks like.
So here's our concept architecture for our rover subsystem. So what the system will look like: it'll look like an RC car with 4 wheels and a cube-shaped body. Some interesting features: it'll be able to operate in any orientation. It's symmetric on all sides. It'll be able to recharge its power source. So on the power source here, we decided to go with radioisotope thermoelectric generator as its main power source, and then we have lithium-ion batteries as a backup, and those would recharge aboard the lander. So the rover will be able to map out the inside of the lunar lava tunnel. It'll be able to collect information about the surrounding environment, such as chemical composition, temperature, and radiation. Why is it a great concept? It's a small system. It's durable and can operate in extreme conditions. So the kind of size there you're looking at is about 30 inches, 36 inches from tip to tip. It can be part of a network of multiple of the same rovers. So the design we went with is kind of approximately 4 rovers would be inside the lander, and then we would deploy all 4 of those to go out in different directions. And then we have a low cost for manufacturing because it's all just similar parts repeated over the whole rover. So here's a more kind of detailed look into the computer-aided design we did for the rover. So as you can see here, we have a radioisotope thermoelectric generator powering the whole thing. We have 4 wheels, and the design for those wheels is based on a Mars terrain wheel that NASA tested. It's kind of a meshed wheel that has the ability to cross over all sorts of terrains. And then we also have these U-shaped kind of wheels that were taken from Boston Dynamics R-Hex robot. So those have the ability to kind of twirl around and dislodge the rover from all sorts of weird situations it might get into with the terrain. Within these kind of empty areas, we'd have a few sensors, including spectrometers. We'd have motors. We'd have like a drill, some sort of drill to collect lunar regolith, other functions that we would need. Yeah.
Thank you.
Thank you.